The next effect that we're going to look at is dielectrophoresis, not electrophoresis, but dielectrophoresis. So what is dielectrophoresis? Well, let's start from a very simple system. Imagine that I have two electrodes, a positive one and a negative one. That means that I will have field lines between these. In this direction, I have an E field. And the field line density between these two will be dependent on the permittivity, epsilon, of the medium. Epsilon m is the permittivity of the medium. Yeah. What happens now if I bring into the system a region, for example, a particle with an epsilon that is epsilon p, yeah, a different permittivity. Well, if the permittivity of the particle and the medium is the same, then the electrostatic field lines will look exactly the same. However, if the permittivity of the particle is larger than that of the medium, that means that the field lines like the particle more than it like the medium. So the larger the permittivity, the more the electrostatic field line like it. So then this particle will start sucking up electrostatic field lines. So then my field picture will not look the same, but instead it will start looking something like this. It will suck up field lines here, like this. And I will get a distorted electrostatic field line. Huh? That is if the particle has a larger permittivity. If it has a smaller permittivity, the opposite will happen. All the field lines will try to go to the medium and will go around the particle. I'm not going to draw that here, but you get the idea. And you also have to understand, I discussed this now from the energy perspective, because the permittivity of a medium is really tells how much the electrostatic field like to be in a certain medium. I can also see this from a charge perspective, which is exactly the same story, but told in a different way. I could say that bringing a dielectricum with a certain permittivity into an electrical field will induce charges. For example, here you induce negative charges on this side and you induce positive charges here. So there's a polarization of the particle. And so you get the dipole interactions. That will actually, this is telling the same story but in a different way. Okay. Well, so far I've seen just two parallel plates and a particle brought in here, and I can see particles with a different permittivity will distort the field lines. How can I use this? Well, not in this type of configuration. However, if I change my configuration such that I still have my positive electrode here, but now I have a negative electrode that is much smaller in size, then I see that my field lines typically will look like this. If I now bring my same particle, I'm going to draw it now as a round particle, it doesn't matter. If I bring my particle in here, epsilon p, again with epsilon p, and here I have epsilon m, and again I say epsilon m is smaller than epsilon p, just for the illustration, then I see again that my field lines will start looking like this. They will be sucked up by my particle. So I see my particle sucks up all the field lines. And now I can see that the more field lines that go through the particle, the lower the energy of the system, because if they go to the particle, they don't have to go to the medium, and they like to be in the particle. So the field lines want to go to that particle. Yeah? So the more field lines I get to the particle, the lower the energy. And now I can also see, if I would move my particle a certain distance dx in this direction here, like for example to this position here, then I see that I will be able to suck in more and more field lines into my particle. Yeah? So in this position, if I move my particle towards the position where I have a higher density of field lines, the energy of the system will go down. Yeah? So that means I have a change of energy per a change of displacement. That means, per definition, there is a force on the particle. This is from an energy perspective. I can say from a force perspective, and I call this force the dielectrophoretic force. Yeah? So a particle with a certain permittivity brought into a medium with a different permittivity and bring that into an electric field with a gradient, then you will see that the particle will move either towards where the highest field density is, or if the epsilon p would be smaller than the medium, of course it would do the opposite. It would try to go here where it has as little as possible field lines. Yeah. So I call this, if it's moved towards the highest density of field lines, I call it positive dielectrophoretic force. If it moves away to the lowest, I call it the negative dielectrophoretic force. And whether it moves to the positive or negative is dependent on this one. Is the medium, the permittivity of the medium larger than or smaller than that of the particle? The force is not only dependent sign-wise on this, but it's also dependent on the size of the particle, about to the third power. So it goes with the volume of the particle. The larger the particle, the more force it will feel. And finally, interesting to see is also that this is frequency dependent. So at certain frequencies, the permittivity may change. A medium may, for example, become larger at lower frequencies or smaller at high frequencies. So this sign can switch depending on frequency. Yeah? So these are tools that I can now use to steer how particles will move in an electric field. And this is used in cell sorting, where, for example, the particles here, then these are cells, and we will see that different cells have different permittivities. For example, a live cell will have a higher ionic content than a dead cell, and therefore the polarizability of a live cell from a dead cell will be different. So you can, for example, in a mixture of cells, like in blood, you can separate out the dead cells from the living cells, or you can separate the large cancer cells away from the healthy, smaller white blood cells, or you can sort away bacteria that are much smaller in size. They will go with the flow, whereas the large blood cells, they will move, they will be dragged to the wall using the electrophoresis. So you'll be able to do cell sorting and this kind of things. And there's actually, in the next section, there's a video that you can watch that illustrates that.